So, hello everyone. People are still coming. So let me start the EVN seminar. This is Anna Bartkiewicz at Nicolaus Copernicus University in Toruń, Poland. I am very happy to welcome you on behalf of the organizing committee to this second series of seminars sponsored by the European VLBI network, focusing on high-resolution radio astronomy. Let me mention a few logistics. You will be muted throughout the presentation, but you are invited to type in any questions you may have for our speaker through the Q&A Zoom facility or in the chat at the YouTube channel. Questions will be answered only after the presentation. Please try to write your question clearly and keep them short. We will aim to get to as many of your questions as we can, and we apologize in advance if your question is not among those we have time to answer. Now, Benito Marcotte from JIVE will introduce today's speaker, Giuseppe Cimò.
Thank you, Anna. I'm glad to introduce our today's speaker, Giuseppe Cimò. As brief summary of his career, he finished his PhD in 2003 in the Max Planck Institute for Radio Astronomy in Bonn. And at that time, he was working on intraday variability of EGN. Afterward, he moved basically to the University of Tasmania, where he continued working on interstellar scintillation mainly. And it was after that when he moved to JIVE in the Netherlands, first as support scientist of the European VLBI network, and then later on he joined the Space Science Group in 2009. And currently he works on VLBI observations of a spacecraft and basically cover all the different applications that these observations can have. And this is basically what the seminar will be focused on today. Simultaneously, Giuseppe is deputy of the Pride experiment on board of the ESA flagship mission JUICE, and he leads at the same time the intraday variability study of radioastron targeted AGN. Basically, he combines that with being involved in the management of different ESA-funded projects like Asterix or Jumping Jive. So with this summary, Giuseppe, the floor is yours to continue the seminar. Thanks.
Thank you very much, Benito, and thanks everyone for being here. I'm start sharing my screen. Oh, okay. Well, thanks for giving me the opportunity to talk about this topic. It's about observing spacecraft. So the spacecraft are the target of our observations with radio telescope on Earth. I'm Giuseppe Cimò. Benito already introduced me. I work at JIVE, and I will present the work of the PRIDE collaboration. PRIDE stands for Planetary, Radio Interferometry, and Doppler experiments. So there are a lot of applications. I will go through all these applications. But it's the work of a team, and I will put the reference to their work in the slides. If you see very nice pictures of planets, satellites, and so on, the credits go to NASA and ESA. All the other plots and so on are from our work. So you see here a picture of the radio sky. So that's how the sky would look if we would observe that in radio with the same resolution of our eye. So you will see a lot of points that could be like a star of our galaxies, and then you see some extended emission and so on. This one, it's to obtain this kind of comparable to naked eye resolution, you need a telescope which is large, about 100 meters at centimeter wavelengths. For example, the Hubble Radio Telescope that recently celebrated its 50th anniversary. So with this kind of telescope, with this very large aperture, you can see the sky has you would see in optical with an optical resolution with your naked eye. Well, of course, we use telescopes, and in optical, for example, we have Hubble Space Telescopes, and you see the image here of a galaxy, that's Sirius A. The blob in the center, it's the galaxy seen in optical with the Hubble Space Telescope. And these big lobes, these red lobes here, correspond to radio emission observed with VLA, the very large array in New Mexico, the US. So you can see already that with a telescope, so which is well, a small array of telescopes, you obtain much more information in radio than, and you see some details that you cannot see in optical. If you want to zoom in, so that was the able image, and it's very hard, well, at the moment to go farther in resolution in optical. We of course are building better telescopes, better and better telescopes. In radio, to go deeper into this radio galaxy, we use the VLBI technique that give us the sharpest view of the universe. So that's the same galaxies as you say, and the small dot in the center, it's zoom in with VLBI, and you see different images here at different frequencies. And on the side, you see the resolution. So you can really see about a size of 2 light years of a galaxy, which is very, very, very far away from us. So VLBI is really allows us to zoom in a very, very, very close to, in this case, the core of a supermassive black hole of a galaxy. The difference of a VLBI array compared to other arrays is that the telescopes are not physically connected. Here you have a map of the globe, and the points correspond to radio telescope of the European VLBI network, and you can see they are spread all around the world. How does it work? You have a signal of a quasar that arrives from very, very far away, and it's detected slightly different times because of geometrical delay, because of the different position in the globe of the 2 antennas. And the data that are collected at the different telescopes are time-stamped with an hydrogen measure at each antenna. And then the data are sent to a processing center, for example, a jive correlator, to be put together and create the sharpened image that we have seen already in previous EVN seminar. Here you have a couple of examples from Cristiana Spingola, and that is another image of the localization of an FRB, and of course the famous image of the EHT collaboration of the black hole. So this is an introduction of VLBI. So with VLBI you can do a lot of kind of observation and science. What we do, it's instead of observing natural sources, which are very, very far away, we observe spacecraft in our solar system. So if you compare this image with the previous one of the configuration of the VLBI, the first difference is that you need to take into account another delay in the arrival, because the spacecraft now it's in the solar system and is very close, and we are in the so-called near field mode of VLBI. So the wavefront is not parallel to the observer or to the 2 telescopes, but the light travel times from, for example, spacecraft to these telescopes, light travel time 1, and from the spacecraft to these other telescopes, they are different. And we need to take that into account in our model for the correlator, so we can make an image of the spacecraft. We use a technique called phase referencing. So we observe the spacecraft and source close in the background. Usually it's a compact radio source, a quasar. So to correct for the so-called phase calibration, to take into account instrumental delays or ionosphere, troposphere, and other effects. But why do we want to observe spacecraft? So what do we do with the spacecraft? So this spacecraft signal is just another source for us, and we treat it as a source. It's a point-like source, and it's a point-like source which goes around other bodies, and these bodies, they have a gravity field, or they have an atmosphere with certain plasma characteristics. So the planetary radio interferometry Doppler experiment tried, so it's able to provide a highly accurate estimate of the state vector of these orbiters or landers by means of the VLBI, very long baseline interferometry. What we observe is the Doppler of the subject, because we observe the radio signal, and therefore we can infer the change in frequency due to the Doppler, and also the position in the plane of the sky of the spacecraft. So we can fix it, we can find in astronomical coordinates, for example, right ascension declinations, the position will be very, very high accuracy of the spacecraft. And what can we do once we have this state vector? We can do a number of experiments, and I will show example of most of these in my talk. We can measure winds on other planets or moon. We can study the internal structure or composition, because we have a probe, which is just a point-line probe in a gravity field. And we can study the variation of the orbit, the predicted orbit in case of a model gravity. And then we can improve our understanding of the gravity field, and therefore, for example, the internal composition of a moon or of a planet. We can improve the ephemerides of moons, which is something very important for a number of cases, and I will show you later why. And we can study the atmosphere dynamics, and since this source is the signal that from the spacecraft is propagating to the interplanetary medium and the solar wind, we can study the interplanetary scintillation. And we can apply the same technique to Earth geodesy, for example, by observations of the GPS satellites around the Earth. And we can even do general relativity and fundamental physics experiments. One famous example of this technique is the landing of the Huygens probe sent by the Cassini spacecraft to land on Titan. Here is an artistic representation by NASA. So the probe detached from Cassini, and this is the Cassini spacecraft, and here is the probe going down. So it was detached by Cassini, and it started to communicate and send data back and forth, back to the Cassini spacecraft with all the data of the landing. And then after the spacecraft landed on Titan, Cassini turned its high-gain antenna to Earth and started to send the data. What we did during this particular experiment, during the landing, it was not an ad hoc experiment, so it was not planned originally by NASA or ESA. And so we just jump in and say we could do this. We can observe the signal from Huygens to Cassini. So when the two spacecraft are communicating with each other, we can observe the signal. So we can piggyback into the inter-spacecraft communication, and we can measure the lateral position of the spacecraft and the Doppler. There was an issue in the onboard Doppler wind experiment, so these kind of measurements helped a lot with the determination of the wind. On the top left, of the top right here, you have a plot with our measurements. I was this experiment was done in 2005. At the time, I was at the Seduna Radio Telescope in Tasmania, observing exactly this landing. Each point here, it's a VLBI observations, and then you have a latitude, longitude, and then altitude. So you can follow the trajectory of the lander while it was going down to the atmosphere, and calculate the wind speed at the higher layers of Titan atmosphere. That was about 430 kilometers per hour. In this case, our accuracy was 1 kilometer in the lateral position. That's because we observed at S-band, which is not very convenient for this kind of observation, and also because it was not an ad hoc experiment, so we need to work with different kind of settings and solve several issues before obtaining this data. So Titan is a very interesting moon because it has some organic compounds, are the oceans of methane, and there is a continuous rain, and it's a planets where astronomers and planetary scientists are trying to find some hint of organic life. Another mission that is interesting in life, in particular the emergence of life around giant planets, is the Jupiter Icy Moon Explorer, or JUICE, that will launch probably next year toward the Jupiter system, and will arrive in around 2030. And there are a lot of experiments on board to try to assess the habitability of the system. One of the experiments is not on board, but it's a ground base. It's our PRIDE experiment. It's an official experiment of the mission. So it's a flagship mission from ESA, so it's a very large mission. It's focused on the Jupiter system, Ganymede, and the Jupiter magnetosphere. And again, try to answer the question, does the Jupiter system harbor habitable worlds? And it has many science objectives. The last one that you can see on the bottom, it's what with the PRIDE experiment we are trying to answer, or at least we want to improve our knowledge of the ephemerides of the Jovian system. In yellow here, you have all the experiments. There are 10 onboard instruments and then PRIDE, and what they will do around the Jupiter system. In particular here, the PRIDE, again, it's the ephemerides, and there are several areas that science cases that these different experiments want to address. In particular, we want to study Ganymede as a planetary object and as a possible habitat. It has oceans behind the icy layers. It has an internal dynamo. It's an archetype of a water world. Also, Europa recently has shown some activity. So there is also an ocean in contact with silicates. So there are very interesting planets or moons for harbor life. The picture here shows an artistic representation of an icy moon. You have the core, and then a rocky mantle, and the ice mantle in the ocean, and the ice crust. All these letters here represent the different experiments of the JUICE mission. PRIDE will help study the atmosphere of this the icy moon, and just complementing the data of the radio science experiments. So we will just provide some complementary data for them, but we will also work on improving the ephemerides of these the icy moons. Then you see all the other experiments try to go deeper and deeper into the core, and then again the radio science and PRIDE could help understanding the nature of the core of the icy moons. So why the ephemerides are important? Because they just fix the planets and the moon into the sky in a particular position, and then you can use all your models to understand better the dynamics of the systems. So you can, in this way, you can constrain the origin and evolution of the system, the evolution in this case of the Galilean moons, and study the tidal dissipations in the Jupiter system, because so these planets are tidally locked, and the better we know their position, the better we can improve our model and understanding better the different forces in place for the dissipations. So it also, so far, we use measurements from Earth, like with the optical telescope from 1873 up to now with the spacecraft observation of the Gaia spacecraft, to do astrometry and try to improve the ephemerides. VLBI will help to also this process and try to produce a better ephemerides for the system. Of course, once this is an interactive process, so once you improve that, you can planning better missions in the future. So PRIDE, it's a particular experiment. I say that it's not an onboard instrument, but it's an experiment because it doesn't require any particular instrumentation on board. It requires a transmitter because we just want to observe a radio signal coming from the spacecraft, and an ultra stable oscillator that will lock the signal, and we want to have a very stable signal to do our measurements, and of course an antenna. None of this is a PRIDE-only device because it's an antenna for communication, a transmitter for the communication, and then there is a radio science on board that will do the typical radio science experiments using an ultra-stable oscillator. So, and JUICE will generate many different data for ephemerides, and we will help with VLBI measurements during the flybys of Ganymedes, Europa, and Callisto, and VLBI experiment during the Ganymede orbit phase. We also get Doppler, and that will complement the radio science data with our Doppler data. These two tables maybe are a bit confusing, but I just want to show you the difference between Huygens, the mission on the Titan that I showed you before, and JUICE. The lateral accuracy, the last column, was about 1 kilometer for Huygens, but for JUICE, using a Ka band, a much higher frequency than the one for Huygens, we can obtain an accuracy of about 20 meters at the distance of Jupiter for lateral positions. And the table down, that's a work from Dominique Dirks from the Delft University, shows the improvement in percentage on the formal error using VLBI data. The IP means the in plane, and OP means out of plane. Of course, if you try to do Doppler measurements and your spacecraft is moving parallel to your plane, you don't have Doppler because it's just rotating at the same distance. But you can do VLBI measurements, and therefore, when the spacecraft is orbiting out of plane, you have these huge improvements in the formal errors. And this is one of the key parts of the PRIDE experiment for the JUICE mission. Now I go through some old experiment or oldish experiment to demonstrate the capabilities of the technique and different science cases. In this case, we have observations of the ESA spacecraft Venus Express. These observations are from 2012, and it was the so-called drag campaign. So for 12 days, and you see in this plot here, from 12 days, the spacecraft orbit was lowered a little bit day by day, going deeper and deeper into Venus' atmosphere. In this way, they measure they wanted to measure, and we did these measurements with the Doppler, the changing frequency and therefore the changing velocity due to the entrance of the spacecraft through Venus atmosphere. Of course, I'm talking about the very high level of the Venus atmosphere. So drag is because you have a slowdown due to the atmosphere of Venus. On the top left panel, you see the telescopes involved. So there are some EVN telescopes in China, plus some other telescopes in Japan and the VLBI network of Australia. And on the bottom one, you see a slight drop in frequency of about 40 millihertz, which is correspond to 1.5 millimeter per second in velocity. So the spacecraft went through the atmosphere of Venus, and the velocity changed of about 1 millimeter per second. And this one can be used for understanding better the higher levels of Venus atmosphere. With regard to VLBI, you have in the top right part of the screen, all these colored dots are images of the Venus Express spacecraft with VLBI in different parts of the Venus orbits. And the bottom plot, you can just barely see, but you can see that all the dots are concentrated around this red ellipse. The red ellipse corresponds to the accuracy, and it's comparable with, or even better, of what the tracking stations of ESA can do for this kind of observation. That's because we have multiple telescopes, not just one antenna, and we can average down our measurements. I go on with the experiment of the Phobos flyby. This was done in 2013, and it was a unique opportunity because the Mars Express spacecraft was passing very close to Phobos, the moon of Mars, about 45 kilometers. So our goal was to make a very high precision positional and Doppler measurements. The PI was Pascal Rosenblatt. At the time, he was at the Royal Observatory of Belgium. And we wanted to reconstruct a max trajectory to constrain some geophysical parameters. The observations were carried out between the 28-29 December 2013. The globes here shows the antennas involved. There were more than 30 radio telescopes globally involved in this experiment, and we observed 26 continuous hours for 3 consecutive Mars revolutions. And so first, the telescope started in Australia, and then New Zealand and Russia and China. Then they moved to Europe, this blue part, and then the red part is the VLBI array in the US. And the configuration, we had primary calibrators, and then a secondary calibrator close by, and then the track of max in those days. So we observed max for these 26 hours, and we estimate the Doppler. Here, I'll show you the Doppler detection for 10 seconds integration. You have the number of measurements and then the Doppler noise. This is a log normal distribution, so you can calculate the mean value, the median value, or the mode. And the mode value corresponds to 1.7 millihertz. So that was the accuracy that we got in our data. And the distance of Mars, that corresponds to 30 micron per second. So we could measure the speed of the spacecraft with an accuracy of 30 micron per second. But that's about the Doppler data. How about the VLBI? So we did the standard VLBI data analysis. I will not go into details. The VLBI astronomers will know the different steps using the standard VLBI data reduction apes. But since we had more than 200 scans of 2 minutes, we use Parseltom, which is a Python wrapper around apes developed at Jive. The blue and red points correspond to our measurements of every 2 minutes in right ascension and declinations. And these are the displacements between the measured position and the predicted max celestial position. And this will give us the formal error of our observation. So what is the accuracy that we can measure the position of a max of a spacecraft at the distance of Mars? In this case, the observation were done at X-band, 8.4 gigahertz. So the precision that we obtained was about 34 microarc seconds in rate ascension and 58 microarc seconds in declinations. That correspond to 35 meters for right ascension and 60 meters for declination. The movie here shows images every 2 minutes of max. So we made a lot of images, and these are the images. And via the task GNFit, we calculate the positions of the spacecraft compared to the predicted measurements. So I mentioned before the atmosphere of Venus. This is a purely Doppler experiment. So we use the data from the VLBI telescopes for Doppler measurements. And in this case, it's not a drag emission, but it's an occultation. So Venus Express was going just behind Venus. Why this is important? So this is, again, complementary to radio science experiments. So we provide some data that could be useful for this kind of experiments. It can characterize the Venus neutral atmosphere. When the radio science experiments do their observations, they have their signal locked to a radio telescope on Earth. So there is a very accurate clock on Earth. The signal is locked to this clock, and then it's sent to the spacecraft that sends the signal back. In this way, they can have very high stabilities, and they can measure. They can do the measurements. However, we observe. We just don't. We're not interested in that part, but we just use the spacecraft as a target, as a radio source. And of course, we want the signal stable, but we can do our observations also when the telescope on Earth is not locked to the spacecraft. Why I'm saying that? Because with this kind of measurements, and you can see in this plot on the bottom left, we can see the signal of the spacecraft also when it's completely hidden by the planets because of the refraction in the atmosphere. So at the beginning, you have the ingress. So when the spacecraft just goes behind the planet, and then it goes down, and then you have a complete occultation. There is from Earth, you cannot see the spacecraft, but we can still observe the signal because it's refracted by Venus atmosphere. And that can give us a lot of information about the composition of the atmosphere. You can make models, for example, refractivity. You can make some assumption about the refractivity of the atmosphere. And then from there, you calculate the Newton number density, the temperature, and the pressure profiles. And here you have some examples of this. I don't go in details here. I just want to show you the last bit on the bottom. There are different colors. So the red one is NO, which is the New Norcia Observatory. It's a ESA tracking station. And we have Badari. It's an antenna of the EVN in Russia. And you can see that Badari goes deeper into the Venus atmosphere. That's because of geometrical configurations. So we could observe with the VLBI, since we have a more telescope or more distributor, a better distributor around the Earth, you can go deeper into Venus and study deeper layers of the Venus atmosphere. We are doing other kind of experiments. For example, we instead of spacecraft, instead of orbiters, we work with landers. Currently, we are working with the NASA Mars Insight and RISE experiment. Is a radio science experiment that is trying to measure earthquakes and try to understand better the internal composition of Mars. So again, we complement the radio science study of the Mars experimentation. We are in strict collaboration with the radio science team. And we do a mix of VLBI astrometry and Doppler. And this is in preparation of another mission, the ESA Lara mission that will go with the ExoMars lander in the next couple of years. You have here now three small plots, windows, and this is to show you that it's very crowded at the moment in Mars. A lot of spacecraft, landers, orbiters, and so on, and we can observe all of them at the same time because they are inside the field of view of our telescopes. So together with the InSight, we have Odyssey and TGO. Then you have Mars Express signal, and there's Mars Reconnaissance Orbiter of NASA, and some others, so depending if they are transmitting or not. And we can do some experiments just observing simultaneously these spacecrafts. Another test that we are doing at the moment is to test our Ka band capability with the BepiColombo ESA spacecraft that is in its route to Mercury, where it will arrive in 2025. This is an excellent testing platform, so we are doing some tests to be ready for the JUICE experiment. These view graphs probably will interest more than VLBI people in the audience. It's about in-beam calibration. So at the very beginning, I told you that we use a background source to do the calibration, the so-called phase referencing. But to do that, we need to node between the spacecraft and the source. So we stay 2 minutes on one, and then we go 2 minutes on the other one, and so on. So we lose almost half of the time also integration times because of this. So we start to do some experiments where you have a calibrator, which is in the same beam, so you don't need to, in the same field of view of your telescope, so you don't need to move from one to another. And at the same time, you have more than one telescope at, one or more spacecraft at the in your field of view. So in this case, you have MAX, which is a polar orbit, and then you have TGO, which is a 74 degrees inclination orbit around Mars, and then you have your calibrator. So you can do a study again of the gravity field of Mars. You remove atmospheric and plasma effect thanks to the phase reference source, and then you can do studies of tidal dissipations and tidal effect. Again, this in preparation of the LARA mission, where you have the lander and then spacecrafts around around Mars, and also for the JUICE mission, because there will be a NASA mission probably at the same time around the Jupiter system, the Clipper spacecraft. On the second panel, this is very technical. It's about Multiview. It's a calibration technique that instead of nodding between your target and your calibrator, you use calibrators that are a bit further away, but in a special configurations and the different kind of integration times. So you can get better calibrations and even improving your integration time. So again, our spacecraft is a probe sending a radio signal in our solar system. And I mentioned several applications of that. And the one byproduct is that this signal goes through some plasma. It goes through the solar wind, and it goes through the ionosphere and the troposphere. And we collected a lot of data. From 2009 to 2016, we observed every single week a couple of times Venus Express and Mars Express. So we have hundreds of data points, and we can apply those to study the space weather. So what can we do? We can do the interplanetary scintillations, we can do solar wind studies, and we can analyze how the scintillations affect the communication signal. So you can tune your spacecraft observation and experimental strategy, and you can even use that to improve your phase referencing cycle strategy. You have two plots in this view graph. The top one, you have the signal of the Venus Express spacecraft at a solar elongation of 8 degrees is the red line, and the blue line is an elongation of 40 degrees. So 40 degrees elongation means that it is farther away from the sun, and the red one, when it's 8, it's very close in the line of sight to the sun, so it goes to the solar wind. And you see the scintillation. So scintillation is a phenomenon that due to the turbulence in your plasma, your signal that should be a stable signal, it varies a lot. That's the same concept of when you look at the sky at night and you see all the stars twinkling. That is because you have some turbulence in the atmosphere, and therefore the signal is not just a stable signal, constant signal, but it just fluctuates up and down because of this turbulence. The plot on the bottom is stated show the scintillations, and and our measurements compared to different kind of contribution. So you have the bottom one, the dark, the orange and the brown is the troposphere, and then you have the ionosphere. The orange one is the ionosphere, and then you have the crosses. The brown one is the troposphere or the air mass, and then you have the interplanetary scintillations. So you can see that your measurements, which are the blue ones, it's what we measure with our radio telescopes. And that's include the interplanetary scintillations on this part of this plot, and then the contribution of the Earth ionosphere and troposphere in this part, the last part of the plot. So why this is important? What can we do with this? We can study, for example, the solar corona. Here you see that our experiments, it's a collaboration with our Chinese colleague Maoli Ma. We are trying to observe MAX, the ESA spacecraft, and Tianwen, which is the Mars or Chinese Mars orbiter. Now that Mars is in the solar conjunction, so Mars, Earth, and the Sun are almost in a line, and therefore the signal of the spacecraft, it goes through the solar corona, and we can make studies of how the signal behave due to the solar corona. It's important because it's still not well understood area of the Sun, and we don't know very well how these interact with the radio waves. And so it was at the moment in China, of course, there are a lot of news about the lander and their spacecraft around Mars. So also our observation made the night news on the Chinese TV. Our goal, again, is to measure the interplanetary electron density fluctuations, so the turbulence in the solar wind, and estimate the solar wind velocity. Sometimes you are far away from the Sun, but the Sun has sent a blob of glass in your direction. These are the so-called coronal mass ejections. Sometimes these reach Earth and cause a lot of problems to our electrical system, communication system, and so on. So this experiment, while we are doing some observation, we noticed that the signal from one day to another changes completely. And we realized that this was due to coronal mass ejection. So it's just a blob of plasma that's by chance passed in front of Mars Express, the signal of Mars Express, while we're observing it. So in one day, the scintillations that we were observing, this variability, increased of a factor of 3. And the total electron constant increase of like a factor of, we measure a factor of 3,000 in total electron constant units. So we could make some estimates on the size of this blob, because on one day it was not there, and then the other day it was there, and then it disappeared again in front of our line of sight, and we calculated that it was a cloud of plasma of the size of 3 times to the 10 to the 6 kilometers, or about 0.02 astronomical unit. Going even closer to Earth, these are observations of the satellites that give us the the position in our cars, in our mobile phone, and so on. So now we have several global positioning systems, GPS around the globe. You have the American one, this is GPS. And then you have GLONASS, Baidu, and Galileo from Europe. So we can observe those with VLBI. In this way, we can tie the terrestrial reference frame to the celestial reference frame by observing these satellites with the GPS. And this is an example. This is my last slides about the using VLBI, well, using the VLBI antennas and the PRIDE technique for fundamental physics, and in particular to measure or prove the equivalence principle of Einstein. So how do we do that? We do that by measuring the so-called gravitational redshift. So we measure the difference in the frequency observed and transmitted because of gravity, in this case, the gravity field. This is done, the PI of this experiment is Dmitry Litvinov from the Astrospace Center in Moscow. And it uses Radio Astron as a spacecraft. It's a VLBI radio telescope that was orbiting Earth. And it has an onboard hydrogen maser. And the goal of this experiment is to measure this violation parameter. So to understand how good is this principle, and if you can measure the validity of the equivalence principle. And these are my conclusions. It's I think I can leave them here. It's just a summary of what we are doing and how we are doing. So we are the planetary radio interferometry and Doppler experiments, and we can do a lot of science applications, and we are collaborating with NASA, ESA, and other space stations to study our solar system, and we can do experiment for planetary atmosphere, space weather, and also fundamental physics. And thank you very much for your attention.
Thank you, Giuseppe, very, very much for this impressive work and the impressive precision. So we have time for 3 questions that we have already. I also sent you by chat for easier. How much dBi, decibel isotropic, gets lost across a certain distance? It regards knowing how to configure the antenna in the first place.
Okay, I don't know exactly the dBi that get lost. Of course, the signal gets weaker and weaker, but we can observe a signal of the kind of Venus Express or Mars Express at very far away from our solar system, so with an antenna of about 20 meters. So if you have like a 20-meter antenna, and then you put Mars Express at the distance of a couple of astronomical units, you can still observe the signal. You can really see the signal.
Okay, thank you very much. And another question. Interplanetary scintillation limits your accuracy of spacecraft tracking as well as the calibrator measurements. How do you handle this? I also post by chat.
Yeah, that's a very good question. In the case of Doppler, we take care of that. Part of that because we try to in our processing we try to remove that. Also, you have to take into account that you use multiple telescopes, and then we can try to see how the scintillation pattern move through your telescopes and try to understand, to model it and maybe to remove it. But for VLBI, I think it's a part of the imaging. So it will cause your VLBI image to get broadened, and there you maybe get less accuracy in your signal, in your detection.
Okay, thank you. When observing GNSS with VLBI, do you also use VLBI phase referencing?
Yes. Yeah. And I read the question. This is totally right. The spacecraft goes very, very fast. And what we did, it's you use multiple calibrators, of course, not of the same. So every time you need to repoint and then you go to a different calibrator. The problem there is not just the fast moving of the space of these satellites, but the strength of their signal. They are very close to Earth and they are emitting a very strong signal, and they saturate the receivers. And not only that, because you can put some attenuation into the receiver, but a telescope has some side lobes. That's how it works. And you have the signal of the GNSS or GPS on the side lobes of your telescopes. It's even stronger than your phase reference calibrator. So it's very hard to do the proper scheduling and then calibration.
Challenging. And can you measure the spacecraft drag?
Because of the solar wind, or because of the just
not specified.
Well, we measured the drag when, in the case of Venus Express, when it was just going down the Venus atmosphere. It could be that any other effects, for example, due to the solar wind, it is so little that we cannot measure. I'm not sure in the future if you think about like solar sail, maybe you can measure the accelerations and so on, but that's something in the future.
Okay. Is any of these experiments possible with single dishes, or all of them require a VLBI network?
If you want to do the lateral positioning, you need VLBI. If you need Doppler, you can do with a single dish. However, it's better to have multiple arrays with a timestamp and therefore a VLBI observations also for the Doppler to rule out to improve the calibration.
Okay. So thank you very much. Thank you for really very, very good talk and interesting. So thank you all the attendants for being with us. And let me invite you for the next EVN seminar on Friday, January 28th. It will be Cornelia Lang. And the title of the talk will be High Resolution Observation of Magnetic Fields in the Central Molecular Zone of the Galactic Center. So see you in 8 weeks. Bye.
Bye, thank you very much.
Thank you, Anna. That was